So for FRQ 3, part A1 asks us to find a differential equation for linear velocity starting from Newton's second law. So for linear, the Newton's second law would be net force equals mass times acceleration. And we know that the force acting on the ring in this case, when it's sliding and rotating, is a friction force. And since this is opposing the linear velocity of the ring, this friction force is going to be denoted as negative. And we know that Fk can be broken down into mu k times Fn. Mu k is the coefficient of friction, and Fn can further be broken down to mg. So this would be negative mu k mg. We have this equals the force equals friction force. We can plug it back into here, knowing that the net force is friction equals ma, and we plug mu kmg in equals ma, so we can cross out the masses, and acceleration is negative mu kg. And we know that acceleration is the derivative of velocity with respect to time, so you write that as dv over dt. And this is the differential equation that we're trying to solve for. So we can set these equal to each other. dv over dt equals negative mu k times g. So that is the equation for linear velocity with respect to time. And then for part 2 of A, it asks us now to find the angular velocity. So we're going to go about a similar way, except the equation, Newton's second law, with angular is net torque equals inertia times angular acceleration, which is alpha. And inertia is given as mr squared. And also we know that torque is equal to the force acting on the rotating object times the radius, or the distance away, the distance it is from the pivot. So again, we know that the force acting on the rolling object is a friction force. But this time, because the friction force is helping the object rotate rather than opposing its motion, it's gonna be a positive force. So that can be broken down to mu k mg, as we already said earlier. So now that we have all this information, we can plug it into this original equation here. It would be mu k mg times, because torque is the force times r, would be mu k mg times the radius equals inertia is mr squared, and alpha stays here. So here we can get rid, this mass is the same mass here, so technically it's a capital M. We can cross that out, and we can cross out the r on this side and get rid of one of the r's on this side. So this is now just mu k g equals r alpha, and to solve for alpha we divide both sides by r. So alpha is equal to, or angular acceleration is equal to uk, or mu kg over r. And again, it's the same process. Angular acceleration is the derivative of angular velocity, so which can be written as dw over dt is the derivative of angular velocity. So we set these two equal to each other. So the derivative of angular velocity with respect to time is equal to mu kg over r of the object. And that is for part A. And now for part B, it asks us to find an expression for the magnitude of the ring as it's sliding and rotating. So part 1 of B asks specifically for the velocity of the ring as a function of time. So we know one of our given formulas is Vf equals V initial, or V final equals V initial plus AT. And we already found up here that when it's linear, linear acceleration is negative mu kg, so we can plug that in. So Vf equals V initial here is given written as V V0 plus, so we will write it as that, and then plug in the A that we have earlier, negative mu kg times t. So clean it up a bit, and the expression for velocity as a function of time would be V initial minus mu kg t. And then for part 2, it asks us now to find the angular velocity. So we can still use the same formula. Angular velocity final equals angular velocity initial plus angular acceleration times time. And already we found angular acceleration here to be mu kg over r. So we can plug that in. Angular velocity final equals angular velocity initial plus angular acceleration, which is mu k times gravity over the radius of the object times t. So that is part 2 of B. And now moving on to part C. It asks us to find an expression for the time that it takes the ring to travel the distance L. So the distance L is given as the distance that the object is sliding and rotating. So we know here when the object stops sliding and is only rotating, the given is that velocity will equal radius times angular velocity, and that is when the object is only rotating and not sliding, which is also where the end of L is. So we can use that constraint to help us find L. So using the formula that's already given here, the one that we already know, is Vf equals V initial. We'll just write that with a 0. Plus AT. So we know that the V final, or the V where the L stops, is going to be RW. So we'll plug this into here. So that'll be RW equals V initial plus acceleration times time. That's linear acceleration. So for W final, where we're looking, we know that we can use this here to find it, and since angular velocity is 0, because at the beginning the object is only sliding, so it's not rotating, so we can plug this here into here. So R mu kg times time over R is equal to V initial plus, and this here asks for linear acceleration, which again we have the formula for that we've already found to be linear acceleration is negative mu kg. So we'll plug that back here for A, negative mu kg times time. So now we can cross out these two r's, cancel out, and we'll want to move the similar terms to one side. So we'll add mu kg t to this side also. So it'll be mu kg t plus mu kg t equals V initial. So it'll be 2 mu kg t equals V initial. And it asked us, part C asked us to find the time that it takes to travel L. So now we can isolate for t by dividing both sides by 2 mu kg. So t will equal velocity initial over 2 mu kg, and that is the time that it takes for the object to travel L, the distance L. At which point after it will stop sliding and only rotating. So that's part C. And then for part D, it asks us to find an expression for the magnitude of the velocity of the ring immediately after it has traveled the distance L. So again, we'll use the formula, common formula, Vf equals V initial plus acceleration times time. So Vf equals V initial, and then now we're going to plug in linear acceleration, which again we found at the very first step to be negative mu kg. And time we just found in C, the time that it takes for it to travel the distance L, to be V initial over 2 mu kg. So we'll plug that in for time, V initial over 2 mu kg. And here you'll see that the mu kg's cancel out, so mu kg cancels out, so we're left with V final equals V initial minus, the negative sign is still here, so minus V initial over 2, which can further be simplified to just V initial over 2, because 1 V initial minus V initial over 2 is just a positive V initial over 2. So that is the velocity of the rolling object immediately after it passes the L section. And then for part E, it's asking us to derive an expression for the distance L. So we can use a common formula for that also, which is Vf squared minus Vi squared equals 2ax. So we already found Vf to equal V initial over 2 squared minus, so V initial squared equals 2ax. And x that we're finding is L, so we can go ahead and replace that with an L. And then we're gonna write this as V initial squared over 4, because we distribute the power in, minus V initial 2. The terms are alike, so we can combine those. V initial squared, can be rewritten as 4 V initial squared over 4, so that we can have similar terms. So that would leave this side as negative 3 V initial squared over 4, and this side comes down and it's still 2AL. And again we can plug in the A equals mu kg into this here, so we're left with negative 3 V initial squared over 4 equals 2 negative mu kg, which is acceleration, times L. And we're solving for L here, so we're going to divide both sides by 2, what will be negative 2 mu kg. This sign will just go here, and that leaves us with L equals negative 3. L equals negative 3 V initial squared over 4 times negative 2 is negative 8 mu kg. You can cross out the negatives, so it'll just be L equals 3 V initial squared over 8 mu kg. And that is an expression for the distance L.